Hello, everyone. This is our project for 3110, and it aims to model no limit hold'em. And you can play a simplified version of heads up, which is called heads up push fold. So basically, your only options in this variant of poker is to either go all in pre-flop or just fold. And by doing this, it makes it much easier for us to actually solve and find true optimal strategy in comparison to if we were working with the full decision space. So just to give you a quick overview of sort of our project tree, we have a bunch of infrastructure which just gets the game of poker like up and running. Cards, decks, dealing, calculating like the best 5 card hand. And then we have some tools for the strategy itself, equity calculator, an equity matrix finder, and the actual convergence itself. And then we also have like sort of a wrapper to allow us to feed those decisions into the bot that we will be playing. So the first thing we need to do is we need to actually calculate the equilibrium strategy. Now, currently, if we go into data, we have an equity matrix, which contains all of the preflop equities between different types of matchups. So it has, I think, a couple thousand in there. If you wanted to calculate those yourself, you would just delete this matrix and then the algorithm would calculate it again. But to save time, we've already calculated it. So
And to calculate it, you would run Nash exact.
yeah, which we're about to do. But if we already have the matrix, then it won't calculate that specific portion again. So this basically takes our equity matrix and uses a variety of sort of mathematical principles in order to derive a strategy. There's not one way to do this, but the strategy we picked, we believe, gives a relatively reasonable result. And the ranges that it's found look like this. So I'll just give you like examples. This is the in position range. So from the big blind, this is your strategy, or like this is the strategy the bot will use. You can do whatever you want. Um, and then out of position, so from the small blind position, this will be its strategy. Now we will run the actual main method. So it's going to ask us for a little bit of information just to set up the game, your name, and then you can choose your bankroll, which is just the total amount of money you have. This is not the amount of money that you'll have in each round. It's just like if you think about playing like $100 poker game, hopefully $100 isn't like the total amount of money you have. Like maybe you have 1,000 or $2,000 in the bank. So now we want to decide our blind structure. We can also choose what we want here. The maximum it allows you to do is if you want your bankroll to be exactly one buy-in. We're going to be smart with our money and not do that. And now we're ready to start. So after it's randomly dealt the cards, we get our hand. To start, we play first. In this instance, it varies. But in this instance, we're going to be playing first in the first round. And we have Queen 9. That's not a terrible hand. So let's see what happens if we just go all in. The bot decided to fold. Um, so we'll play another round. And the bot decided to fold again. We were the second to act this time, switches every round. All right, Queen 3 suited. Seems reasonable. So you can see that the bot has a sort of strategy. It does play like sort of more conservative from the in position. This time the bot decided to go all in. Now 8-7 offsuit. We can see our cards up here and bankroll stack and everything. It's not a great hand, but just to see what happens, let's just put it in and sort of see what that looks like. It's gonna deal the board out. In this instance, the bot has ace king suited, so it makes sense that we lose. And yeah, so we lost our buy-in this time. You can also see that a nice feature that we implemented is that it will show the user their equity. So you can see that against ace king suited, we have around 36% equity. We're supposed to win around 36% of the time, which was not this instance. And this is nice for the user to see, but the solver also uses this when calculating its strategy. This is a pretty good hand. Folds. We're gonna be calling with the king 10 suited. And yeah, we win this time. That's nice. So we have top two pair. And so you can see that it sort of has like a decision-making capacity. Like it tends to go all in with some small amount of bluffs and mostly good value hands, which is generally good practice. Now, in this project, we're not going to claim that the bot ranges are perfect. Certainly, like a very good poker player could exploit this bot and win money off of it. But in general, given the constraints of this project, I think we're very happy with the results we've been able to achieve. So I'm gonna exit out of the game. If you were to play this to until like you lost all your money or the bot loses all its money, it'll say you lose and the game will finish. And or you could just end the game yourself. So I guess finally, we'll just go through the README very briefly, and we can explain like different parts. And Rohan and Mihir can also like sort of pitch in. So um okay. So we have a couple of different algorithmic components to this project. Um, Here, if you want to sort of
Yeah.
explain like how you connected the like ranges to the actual bot.
All right. Thank you, Sucheer. So, one of the things you'll notice is that the regions itself, they're outputted in both a JSON file and a input, in position JSON file and an out of position JSON file. In position stands for the person who shoved, and out of position stands for the person who's almost receiving it. Um, as such, we used a Yo JSON module, which basically is like a third-party module that basically would help us facilitate with the reading and input of a JSON file and converting it to a map of a list that we would be able to extract data or information from, right? If we go back to the JSON file, we can see that the organization of it is based on the cards itself. Yep, the cards itself, given that the cards are the first character of the card and the second character of the card gives a pair, and then the third is an O for standing for offsuit and an S standing for suited. And this would produce like a frequency, right? Frequency would be the percentage of times or the probability that a one would win given that hand of cards, right? So given this, we would then implement from that frequency or probability, we would then ask the bot to produce a decision based on that probability. In that, if say you have, um, for example, double aces, you should probably go in 100% of the time. So the bot would then 100% of the time decide to go all in. However, if you had something closer to maybe um, a pair of sevens, it would only go in 95% of the time, and then 5% of the time it would decide to fold, uh, just because in case that um, to be able to show like the bluffing aspect of it, as well as the chance that the card could be worse, you know?
Yeah, to like expand upon that, basically what the bot is aiming to do is in addition to making profitable decisions, like expected value wise, it's also attempting to balance. If it only uses like one set action with every single hand, what will happen is that it'll become exploitative. An observant player will notice these trends and be able to exploit it. So it wants to mix between different similar EV decisions in order to produce a strategy that is unexploitable. So you can see like what these probabilities here represent is if a bot is in a given position and it has a given hand type, this represents like the chance that it will choose to either go all in itself or call the all in. And
Yep.
in comparison, the equity matrix is what it uses to calculate this strategy. It just represents the overall win rate of its hand against all the other possible hands that the opponent could have. After this, I think Mihir, I think he would like to explain like the front end aspect.
Yeah.
Like how it looks so nice.
Yeah, of course, of course.
Or sorry,
So,
not Mihir. Rohan.
Rohan, yeah.
No worries, it's all
Um,
good. Yeah, so the front end aspect is kind of how we tie it all together and present it out to the player. So we saw earlier throughout the gameplay that we have animation show. So one key thing that we learned a lot about through this project was using ANSI terminal. So we had it to be colorful, so that's easy and a little more interesting to use. Also, we have the animation show. So when the cards are being dealt to the user, there are two cards dealt both to the bot and to the actual player, but we only see the player since that's who we are. And then should both players, player one and player two, the user and the bot, they both go all in, then we'll see 5 cards being shown in the animation of filling out the river. So the way this structure kind of works is we have various infrastructure to show out this game. So we have card.ml. So that card basically shows all the types of cards that we could have. So this shows all the ranks, all the suits. Also, we have deck, which shows the full 52 card deck and ensures that there are no copies of cards within the deck. And also we have hand, which consists of the 2 cards within the user's hand and also the 5 cards on the river. This also helps us choose who actually won the game. So this is a hard set algorithm from the beginning, which is dead set on the rules of poker. So basically the aspect of the algorithm doesn't see the 5 cards on the table. It only sees the 2 cards of the user and the 2 cards of the opponent. From there, it'll make a guess, basically an educated decision on what cards will be on the table and if it'll win based on the table cards. After this decision is made, whether to go all in or to fold, the table cards show out, and then the pre-built algorithm that we built in the infrastructure decides who won the game based on the predetermined rules of poker. So that's essentially how it works, and also the visual aspects as well.
all right, thank you, Ayan.
So finally, just to round off with like one more minute, I'll just go over something like kind of cool about how we optimized this project so that it'll actually like sort of run in like a reasonable amount of time. So when you're calculating equity, a naive way to do it is to sort of just use like a combinatorial approach. You just enumerate through everything, all possible boards. Now, this is 48 choose 2. This is a ton of combinations. It's prohibitively a large space because in a single matchup, it'll take you a couple seconds just to calculate the equity of that one matchup. And if we also use a naive approach to calculating matchups, there's about 1,300 possible starting hands. If we cross that with another 1,300 of the opponent, that's about 1.7 million matchups. And we're calculating 1.7 million boards for each. This is about 3 trillion combinations. And this is prohibitively large. We use a couple simplifications to get this to run in a reasonable amount of time. First, we aren't enumerating over every possible board. Instead, we're using like a Monte Carlo approach, which basically means we're just random sampling some amount of trials. And we're currently using 10,000. You can actually prove that the error bound for this is about 0.5% or lower, which is an acceptable error bound for us, especially given that there's a large amount of matchups. So it's not going to affect the overall strategy that much. The second simplification we use is that we use this thing called bucketing, which basically means if you go back to the ranges here, what you'll notice is that we have this category of hand called ace-ace. Notice that when you're actually dealing out cards, ace-ace is not like a single hand. You can have an ace of hearts, ace of spades, ace of diamonds, ace of clubs. There's 4 choose 2, 6 suit combinations for ace-ace, and with every other pocket pair, there's 16 combinations for offsuit hands, 4 combinations for suited hands. Instead of calculating each of these independently, since they have the exact same equity pre-flop, we simply bucket them together. We choose one representative combination for ace-ace, one representative suit combination for king-king, etc. This cuts us down from 52 choose 2 squared all the way down to 169 times 169. If you look at this matrix, this is a 13 by 13 matrix, so that should be pretty intuitive. In total, this like saves us around 4 orders of magnitude which is a massive difference. With that difference alone, like instead of our strategy taking months to converge, you can do it in under half an hour. So yeah, and in addition to that, OCaml itself is like a pretty fast language. But yeah, I hope you guys enjoyed our project demo. Thank you.
Thank you.
All right, thank you.